Welcome everyone. I'm Daniel, and the work I'm presenting here is the result of a collaboration between my institution, Universidad de Málaga from Spain, and the University of Texas at Austin, institution where I made a short research stay time ago, for which I thank Jeho and Professor Batory, as they taught me a lot and I had lots of fun. In this work, we develop a tool that supports feature models with numerical features and arithmetic constraints. We change a bit the title, transform by support, so it allows you to understand better what this work is about. And why we did decide to use product lines for a software reuse conference? Well, as you know, first of all, developers have always reused sections of codes and programs for productivity. And software reusability is an intrinsic part of product lines. What is a product line? Simply a collection of common features that forms a software family. Those features are parts of a code, hierarchical increments in the functionality of the software. If we compose them, we get the software. We represent product lines as a feature model. First of all, it defines all the features and the relationships, the compatibility, etc. But we can also generate the product space, starting with the model. That's the collection of software in a family. Hey, SPL reasoning yields practical software reusability. That's the main objective. Classical feature models, the ones that were developed time ago and the most common in the literature, are boolean feature models. And they can be translated to propositional formulas. Why? Because they both deal with propositional logic. A classical feature model is formed by binary features, true or false, and Boolean relationships. You have several of them in the example there, like ANDs and ORs and alternatives, what we call XORs. The example is simple. It's a hello world software that we all use when we started learning programming. We have the language, the libraries, and the functions. And there are some compatibility between the languages and the libraries they can use. That's the constraints down below. How do we translate them into propositional formulas? Well, features are the variables in a propositional formula. Simply, we can see a small translation there. Hello world is equivalent to having language and a function because they are mandatory. Then library is optional. You can distinguish that by the white dot in the relationship. Then it implies hello world. If we go on, so on and so on, we end up with the function that is an OR of print and write, printing and writing to a file. So it's an equivalence of having one of those of both at the same time. And you could think, well, great. And why is he explaining this? Why propositional formulas? Well, first of all, propositional formulas are used to propagate constraints. Also, with specific reasoners, they are called solver tools. We can find valid configurations of a formula with a such solver, whether it is one configuration, all the configurations, a range of configurations. But the most important, we can efficiently count the configurations that satisfy the formula with sharp such solvers. They're specialized for model counting of a propositional formula. And they do it really, really fast. And why counting? Why it's so important? Because it is critical to the most accurate algorithms to find near optimal configurations of large spaces for a given workload. I can give more details about this optimization offline, but the work that I used to learn about this is the one referenced there, that obviously it was provided when I made the research stay at Austin. Sadly, classical feature models and propositional formulas are not enough. To represent real-world product lines, we need numerical features and arithmetic because that's relationships between those numerical features. There we provide an example. It's not software related, but it will allow you to understand easily what are numerical features in a product line. We can see there we have different types of aircraft, and they have a numerical value. That means we will count how many of them are. Then we can have a constraint where we say we don't want more than 40 of all of them together. That's numerical, that's features with a numerical value. Consequently, simply put, numerical features are features that could have a numerical value. But hey, think about this. They have a dual domain. They still have the classical part where they can be present or absent in a configuration, but also they could have the numerical value, and it could be negative, positive, or zero. Think about this. You have a present feature in a configuration, and it could have a negative value, and that's okay, or positive or zero. It could be also false and have a value, for example, a constant value, but that won't count for anything of the configuration because that feature is not present on the configuration. Then we will have a mixture of constraints. It could be logic operands, like AND or XORs, cardinalities, implications, alongside inequalities, and alongside mathematics, like the typical arithmetic operands like addition, subtraction, multiplication, division, and modulo. Another example of a mixture constraint, the addition of the cache memory and the garbage data in a program. It should be less than the available RAM memory. And the problem is, how do we get from numerical feature models that contains numerical domain into propositional formulas that they work with propositional logic? For that, we found in the literature bit blasting. It was invented by the logic community a long time ago, and what they do is to encode numerical values as binary bits, as bit vectors, which is our approach to make scalable counting tools supporting numerical features and arithmetic constraints. The solution, a tool that we developed that allows you to model and bit blast automatically numerical product lines by encoding them as Boolean features and logic operations in the form of a propositional formula. And finally, we are so proud to present you Nemo, the tool that we've developed. With Nemo, you could define a numerical feature model and then automatically convert it into a propositional formula that then, with specific solvers, like SAT or SHAP-SAT solvers, you could optimize, constraint propagate, count, generate configurations, etc. In Nemo, we use bit blasting to represent numerical features and the arithmetic operations by k-bit Boolean vectors. Think about this. We are not just translating the features into bit vectors, but also the arithmetic operations. Those are the most critical and most complex ones. Nemo supports features of domain Boolean, integer, and natural, which is granted by default. We can define constant features with a value that cannot change, enumerated features with specific values. We will give an example in the next slide, and ranges of values. Then we can define different cardinalities or mandatory and optional relationships, where the optionality is by default. Finally, the merge of the logic inequalities and arithmetic constraints explained in previous slides. Okay, that's so interesting. But Daniel, how do we actually perform bit blasting? For that, I provide you two examples. One, that two numerical features A and B are equal, and the second one, similar, but greater or equal. We don't have much time on this conference, then for more complex one, I refer you to table 1 of the paper, where you will find additions, multiplications, division, and a more elaborate explanation. Each numerical feature goes from a range from -2 to 1, because we are using a 2's complement sign integer. That means we need 3 bits, 1 for the sign, 2 for the values. How do we check that all the bits, that the two numerical features are equal? Then all the bits must be equal. And what's the propositional formula? A direct transformation of an equality to an equivalence. That's converted. Second one is a more complicated one. First of all, we will be checking that the first bit, that's the sign, the highest order bit, is less in A than in B. Why? Because 0 means a positive number and 1 means negative number. Then we will be checking a sequence of the left bits that are at least equal or greater. How do we translate that to propositional formulas? Well, a less A of B is a not A1 and B1. Then the equalities, we already transformed them in the first example, is an equivalence. And for the greater or equal, I can tell you it's an equivalence, more details on the paper. Then we already have the propositional formula of a numerical feature constraint. Okay, Daniel, I'm getting overwhelmed about this. Don't worry. Now I present you the tool in a nutshell. Nemo is a tool that it performs a bit blasting. Of what? Of a numerical feature model specified in a Nemo syntax, and the output is a propositional formula in a standard Dmax file, which I will give details in the next slides. Here I present you an example and also a summary of Nemo's input syntax. Here we are defining features. Most of them are numerical features. The first one is a constant with a value of 3. The second and the third ones are two different numerical features, but with the same range of values, 0 and 3. That's because Nemo is so smart that an undefined lower bound is considered a 0. Then we have feature D, that is an integer between -2 and 1. Then we have an enumerated feature that it can take the exact values -1, 2, 4, or 8. Then we have a boolean, simply regular feature, and then a predefined. That means we are extending an old feature model with numerical features. Then we have the constraints. First constraint, and we can see written the constraint in the listing text. We are checking that G or if one of the two Boolean features must be present on the configuration. And then we have an arithmetic one, where A multiplied by B must be greater than Z, and that implies that Boolean feature F or E equal to D must exist. Now I present the output of Nemo. That's the Dmax file I was talking about in previous slides. For this example, I decided to use a simpler constraint, just size-wise. This one is A, numerical feature A equal to numerical feature B, requires Boolean feature Z. And A and B just goes from -1 to 1, so we just need 2 bits for each. The first portion of the Dmax file are the comments. C means comment. And they are identifying the different bits with respect to the variables. For example, the 2 first bits of A, the 2 bits of B, and the citings. What are the citing variables? Those are extra variables that we created in the encoding process, but they don't distinguish different configurations. Okay, we preserve model equivalence and model counting. And then we have the feature, Boolean feature, that is just a single bit. Then we define the problem. It's a CNF format of the propositional formula. We have 8 variables and 14 clauses. Then each clause is identified ending by 0. That means finish that clause and start the next one. And they define the constraints of the formula. The first one is real example. We are telling not the second bit of A. So the second one is not the second bit of B, and so far and so on. To evaluate Nemo, we present 2 research questions. First one is related to how variable is Nemo, depending on the bit width of the numerical features. And the second one is related to the propositional formula generated, if it is faster to count or not. The central question is how fast can Nemo count compared to existing approaches or tools? Natively, we embedded SharpSat tool to count the number of solutions to a propositional formula. For the first question, we present the first set of results. Here, we tested 5 different constraints: an addition, a subtraction, multiplication, division, and modulo of 2 numerical features, and that means an equality with a third numerical feature. On the left graph, we check the number of clauses depending on the bit width. And on the right graph, the counting time, the time that we need to count the configurations of that formula, also depending on the bit width. As we can see there isn't a relationship between number of clauses and counting time. Why? Let's take a look at the lines. The first line, it's from the multiplication, which generates the maximum number of clauses. But on the right side, we can see that it's not really slow to count. On the other hand, division and modulo, they have average number of clauses, but they are really, really slow to count. For the second set, we base the new 4 constraints on the addition that we presented previously. Actually, the second line is an addition, as presented before. First one, it's a nested constraint. Why nested? Because we embedded the addition into a requirement of a feature D. The third one is just a duplication. So when we have parentheses 2, it means we have A plus B equal to C, and also D plus E equal to F. And the same for 4, in this case, 4 duplicated constraints. We can see how the nesting on the right graph is taking the longest to count compared to the others that the difference are negligible. On the right side, we can see that the number of clauses generated are more for the duplication than for the nesting. What can we take new from here is that it scales up to 12-bit width while counting under 10 seconds. And also that nested constraints are set at the slowest to count. Now we'll be checking real-world converted numerical feature models into propositional formulas and counting them with different reasoners. And check if counting time is better or worse for Nemo formulas. We expect it to be better. The tools that we use for comparisons are an SMT solver, C3PI, a CP solver, Claffer configured with Choco solver, and SharpSat. That's a SharpSat solver. Mind the difference between the symbol and the text sharp. For that, we chose 7 real-world SPLs taken from other works, and they are ordered by the size of the configuration space. We can see how the first one, well, 11 features, more than 2,000 configurations, that could be considered large, but we have even colossal ones, like 10 to the power of 12, 10 to the power of 45 as configuration space. That means the number of configurations. And here we present the most expected results for Nemo. Any numerical feature model, even the real-world ones, even the colossal ones, converted into a propositional formula by bit blasting, is really, really, really fast to count compared to any other tool. You see the numbers there. Additionally, while C3 and Claffer natively supported numerical features and arithmetic at some degree, even with, let's consider them large but yet not colossal product lines, took so much time that we didn't know if they hung or they were just still counting. It goes even further than hours, okay? Hence, SharpSat counts the configuration of Nemo professional formula considerably faster some SMTP or CP solvers can do, even if they natively support numerical features. Now we need to check the scalability of Nemo as a tool. What do we mean with that? How much time it takes for Nemo to encode a product line into a propositional formula. For that, we take all the constraints that we took for RQ1 and check how much it took for them to count, and also increasing the bit width as we did before. As we can see, multiplications take the longest to convert, and then the division. That is expected. But also what takes even more are the duplications. In this case, the A plus B equal to C 4 times. That takes even more, double than the multiplication, which we didn't expect it at the beginning. Hence, all transformations finished below 40 minutes for up to 16-bit width. Also, the relationship between encoding time and the number of clauses is there. Conclusions after this work. First of all, Nemo models automatically optimize and transform numerical feature models. Why automatically optimize? Not just because of the configurations that we can do then with the counting. Also because we develop Nemo in a smart way that it automatically adjusts bit widths to be the minimum, and also the carry bits. You can see more about these optimizations of the tool and the model in the paper. Additionally, it bit blasts numerical feature models up to 12-bit width without any overhead. It also provided support of numerical feature and arithmetic for current SAT and SharpSat based reasoners. Finally, SharpSat, the solver, counted Nemo's colossal numerical feature models under 0.01 seconds. That was really fast, which is something feasible for solvers that are not shard-based. Future work, we would like to support more domains and constraints like floating points, real domain. That's tough, but we are getting there. We want to also implement other bit blasting encodings, not for faster encoding, that is the citings encoding, but for faster to count propositional formulas. So we want even to go lower than 0.01 seconds, probably going to milliseconds. We want to define a complete modeling language for extended numerical feature models. What we have now, it's a syntax, but not a concrete, proper presented language for modeling. And also, we would like to provide a graphical interface. Everyone likes that. We thank all these projects for their fundings. And merci beaucoup. I'm open for questions, and thank you so much.